In this third example of trussless machines and frames, note that we don't have a truss, that's for sure. We have a lot of pin-connected members in this backhoe, but we don't have a frame. Frames are stationary, machines are mobile. So what we got here is a machine, and we've got the bucket that is digging into the earth, and the earth is pushing back 20 kilonewtons, and we're going to look at the effect on the whole system based only on this 20 kilonewton horizontal force that's pushing back on the bucket. So we're ignoring the self-weight of all the components here. And what we've been particularly asked to find here is the resultant force in the pin at B as located here. Now, one of the challenges of these systems is certainly just trying to navigate through all the different pieces and what do you have that is useful and not useful, meaning not needed, and what pieces or just the dimensions are sometimes challenging. So note here that if we want the force at the pin at B, we want to pull that, but we have to be able to pull everything off, just kind of like a method of sections. And so if we pull the pin at E and B, we have a nice little simple system that's just this whole bucket and hydraulic cylinder and linkages and boom and all the rest of it here. So might as well just go for that sort of part of it. Do a free-body diagram of this whole assemblage that's out there. We don't need to represent every last little piece of it in the sense of the grand detail of it. We just need to get the relative kinds of pieces of it together. So I'm going to simplify all of this quite a bit, really almost just draw an outline of the various pieces, and that will be good enough. We've got all that just sort of solid stuff in there. And now we got the applied load that's horizontal of 20 kilonewtons down here, and we pulled a pin at B, so we're going to have two forces. And then we got when we pull the pin at E, we got to notice that we have a hydraulic cylinder. It's pin connected on either end. It's only connected at two places, no other load, so therefore it's got to be a two-force member along the line of action of ED. Now we might want to guess intelligently guess what direction we think it's going to go. If we were to some moments about point B, we could then figure out that the 20 kilonewton load when we pin at B wants to spin everything in a clockwise fashion, so that means that ED, the hydraulic cylinder, is actually going to be going in the other direction. And that means it's headed downwards and to the left. So that means BX, not BX, yeah, BX, that's right. BX has to be going to the right, because with EDX going to the left, 20 going to the left, that's the only way to equilibrate the B. And then because ED is slightly headed downwards, that means BY would have to be heading upwards. Right? And we want both BX and BY. We don't know how they resolve themselves. There's not a two-force member here. It's a very complicated linkage back in here. So all I know is that I have two independent pin forces there that will resolve into a single one. And we've intuited which directions the components have to be acted. So if we some moments about E, the problem is that I'm going to get two unknowns that are independent in it. If we some moments about B, I'll get ED, but I won't have the things I want. Well, that's a conundrum, and that's what you've got to solve in your homework. You can take a look in the textbook and find out how they approached finding ED. This turns out to be a sample problem from Miriam, Craig, and Bolton of 4/9. So you get another kind of perspective of things, but I'll let you then creatively brainstorm how you might go about getting BX and BY in the most direct, straightforward